Hello. You will recall, I'm sure you will, that from the last video we looked at, what were they? A public wrapper, a private overload, that together, the pair of cousin functions with the same name but different parameter lists, were doing what the old print debug that went through a for loop used to do, except doing it in a really strange and wonderful way. This is video 5, picking up where that one left off. I think it is very important for us to do a trace and see how this does what it does. And you are exactly right. For us to be able to trace it, we've got to have a linked list to work with. So here we go. Let me see if I can. I should have done this in advance too. This, by the way, all I did was copy what was down here from video 4 up here for video 5. So I didn't change anything. At least I better didn't. That's the private overload. That's the comment. Print lazy debug. Wants a pointer to a node. If p is 0, get out of here. There's nothing to do. Oh! Copied fast. Here's a missing curly bracket right here after the return. Sorry about that. So it should be if p double equals 0, return close curly bracket. That looks like a 3. Man, this module, what is it with this module? Module 2, I do not love you. Okay, if p is 0, return close curly bracket. Otherwise, we're still here. Print out the data and call the function recursively. I shall not shy away from that word. We're calling it recursively. Here's a linked list. Head, cursor, tail. Now, I can put those as closed boxes, violating my own deeply held conventions, because since this is an accessor, it's not going to change these. So once I put in pretend numbers here, maybe hex 100, maybe hex 500, and maybe hex 800. I don't know. I just made those up. You can make your own. Anyway, whatever. Here they are. Empty head node, garbage empty head node that lives apparently at address hex 100. This points at the first real node in the list. And let me see. Let's put 3 real nodes in the list if I've got room. 1, 2, one more. And 0 is the next pointer. By convention, fill in some data. Mo, Larry, Curly. There's no significance to those names. I just made them up out of thin air. Let's say that lives at hex 100. This one has to live at hex 800. No choice. With what I have already for the tail pointer, because the tail points at the last node. Review of pointers and picture drawing and all that stuff. Oh my goodness, the picture drawing becomes so incredibly important. Okay, cursor, hex 500, maybe cursor points at Larry. So Larry's address then would be the hex 500. That part I did make up. And Mo, maybe Mo lives at hex, oh, Mo is bad. Let's give him a bad address. FF0. Yeah, that looks pretty evil. So got some blanks to fill in. That means that head arrow next. There's not much space to write here, but that's hexadecimal FF00. I'm going to have to widen it a little bit. One moment while I turn sideways. FF0. Head arrow next. Points at Mo. And even though it doesn't look like it, that next pointer there has value FF0, because that's the address of Mo. Mo points at Larry, hex 500. I just realized how stupid it was trying to turn sideways to do the X. X turns sideways automatically. There. Is sideways and upright. I learned something today. Larry lives at hex 500. That's why Mo's next pointer has hex 500. Larry points at Curly, so Larry has, look at me, I can do an X without turning sideways. The A is not so easy though. A, 0, 0, that's not too bad. Already a review. Here's a complete picture of the linked list. I'll read it back in case it's too small to read. The head, the value of the head pointer is hex 100 because that's the address of where the empty head node lives. In the heap, look at these technical terms I can use now. This was dynamically allocated out of the heap. At hex FF0 is head arrow next. That means that's the address of the first real node in the list that has data value Mo. Mo's next pointer is hex 500. The next real node in the list is Larry, living at hex 500. Larry's next address, hexadecimal A00, is the address of Curly, also the address of tail. And as it turns out, since this is a mutator, who cares where the cursor is? You can point the cursor at the empty head node, at the end, wherever, it doesn't matter. Don't know, don't care. What do we care about? Let's see if we can do a trace of what this function does. Now, how are we going to trace through a recursive function? You know what? To be able to trace through a recursive function, we got to keep our eye on what's going on over here in this thing that looks like a gigantic variable. It's not. This is the program stack. Show of hands. Who wants to tell me what kind of stuff goes in the program stack? The nodes. Oh, no, no. These nodes, they live in the heap. They're not in the stack. The stack is where everything, all the intimate details about one particular function call live in a box called the stack frame. So the stack frame holds the local variables, the parameters, all that stuff for one particular function call. Now, there is a missing function up here that is such a lazy function that is not even worth taking up whiteboard space in this example. But you'll recall there was a public wrapper called print lazy debug, but really, mental note, all it was doing, if you recall, or look back at the video or look at your notes, all it was doing was passing in head arrow next to jumpstart the ball rolling on this recursive function. So if it passes in head arrow next, let's see, in the picture, head arrow next is hexadecimal FF0. So in this first stack frame out here, I'm going to put that P is hexadecimal FF0. And I'm going to put a little mental note to self here. This is not actually in the stack frame, but I'm going to put number 1, meaning that's the first call to this function. There will be more than one call, heads up. But this is the first call to this function. Let me catch up with where we are. All of this, I'll make this really big so it can handle lots and lots and lots of function calls. There. Print lazy debug got called, passed in a value for P, which was head arrow next, which is hexadecimal FF0. So that's the value of variable P in the first stack frame that we're paying any attention to. I stuck that on at the end because this is not the top stack frame. The top stack frame is the main program. The main program has called our public wrapper. Each one of those has its very own stack frame in the stack. I'll put some dots up here to indicate that's not really the very, very first thing in the stack, but it's the first thing that makes any difference to us. Now, why would we want a picture of the program stack, something so technical, when all we're trying to do is figure out what this C++ code is doing, for crying out loud? Watch carefully. We've got to refer to this over here. This is our variable trace of what's going on where and when. If P equals 0, oh, wait a minute here. There's P's flying around all over the place, right? That doesn't sound good, does it? If P is 0, let's just check and see. This is the only P we can see. This video is going to sound really weird. This is the only P we can see. It has value hexadecimal FF0, the address of head arrow next, and that is not 0. We don't return. We're still here. So, in our variable trace, let's see, the very first thing we see out is P arrow data. P arrow FF0. I'm not going to draw an arrow or this picture will get absolutely hopeless. It'll look like multicolored spaghetti. FF0 is pointing at this node. So when it prints out P arrow data, it prints out Mo and follows that with a blank. I'll put an underline character to remind myself that a blank was printed there. Here's where you might want to pause the video and drink a cup of real strong coffee. Maybe I should do that myself. Look at this. This is our first recursive call. Let me tell you a funny little story. How can the system possibly get away with allowing us to have a function call in itself? How can it keep up with all that? Here's the funny story. The compiler doesn't know that recursion exists. Ha ha, isn't that funny? The compiler is blissfully unaware that we have functions that are calling themselves. Here's the deal. We are familiar with functions that call other functions to do part of their dirty work, right? Main program calls function A calls function B calls function C. C is at the top of the stack. It's the only one the system can see with all its local variables and everything. When it's done, pop, it comes back to function B. When function B is done, pop, it comes back to function A. So here was that in a nutshell. Main calls A calls B calls C. As we return back through them in reverse order. C returns back to B returns back to A A returns back to main. Same thing, except we're going to have A calls function A. A calls function A. Every time we make a function call, the system says, you know what? I think this, as far as I know, that's the first time we've ever been to function A. I better make a new stack frame for it, for all its local variables and parameters. So it doesn't know that we're calling the same function over and over. It treats it as if it has never been to that function before. So watch this. Here, we printed out the data, and look at this. Print lazy debug. Here we are just calling a function as far as the compiler can tell. We're calling a function, and we're passing in the value of p arrow next. What is the value of p arrow next? Here's p. P arrow puts me here. Next has value hexadecimal 500, also known as the address of Larry. Let me do that again. We're passing in p arrow next as the parameter value. P hexadecimal FF0 arrow next hexadecimal 500. We're passing that in to this function out there somewhere. I don't know where it is. We've never been there before. We're passing it into a function called print lazy debug. We're passing in hex 500. I'm repeating this over and over so that I don't forget it. Once I get this tangled up, there's just no hope. Hexadecimal 500, that's what we're passing in. Okay, here comes my hexadecimal 500, looking for a place to land in a parameter to some function somewhere. Where is the function? Oh, look, here's a function named print lazy debug. And it's accepting a parameter that it's going to put in variable p. Brand new function call. We've never been here before. That's the first time I've ever seen this function. And someone gave me a hexadecimal 500. I've got to make a new stack frame. New function. P, hexadecimal 500. This is what's called dormant. Dormant in the stack. It's hibernating for the long cold winter of microseconds. That is the only value of variable p now that the system can see. And as far as it knows, it has never been to this function before. It goes through the whole thing from top to bottom. Just so casually, has no idea what's going on. If p is 0, you know what? P is not 0. It's hexadecimal 500. So it won't return. It'll stay here. See out, print out p arrow data. That's the only variable p that the system can see. That's at the top of the stack, and the top of the stack is where all the local variables and everything are that the system is paying attention to right now. P arrow data. 500 is the address of node Larry. So 500 arrow data, hex 500 arrow data is Larry. And it prints out a blank afterward. Oh, look, it calls another function. What function is that? Well, it's a function called print lazy debug. It's passing in as its parameter value, p, which is hex 500, p arrow next. Hex 500 arrow next is hexadecimal A100. So we're passing in hexadecimal A100 to a function called print lazy debug. Brand new function, brand new stack frame, incoming. Here's the function that we're calling. And clear your minds. We've never been here before. Let's see what this function does, just out of curiosity, since we've never been here before. We just now got a value of hexadecimal A100 passed into us to be the value of variable p, hexadecimal A100. Are you 0 hexadecimal A100? No, no. A100, anything that's non-zero is non-zero, so that will be false. It does not return. It does, however, stay here with the implicit else and print out p arrow data. A100 arrow data is curly and a blank. And print lazy debug. It makes a function call, passing in p arrow next. P arrow next. Let's see. Here's p, A100 arrow. Oh! Danger, Will Robinson. We're passing in a 0. Yikes. Maybe we should have an if up here. If p arrow next is not 0, then make that function call. You know what? We don't do that. We don't do that. That actually complicates the code ridiculously. And it turns out we don't want it. We don't need it. Let's see what happens. We pass in a 0. And yes, the system makes a brand new stack frame. And as far as it knows, it has never been to this function before. I keep saying that over and over. That's actually a very good way to think about recursion. Each function call is fresh as a daisy. And the system, for all it knows, it's never been to that function before. Why is that so healthy? Because recursion, as we're going to find out when we're designing our own recursive algorithms, and yes we are, recursion takes an extremely local view. It pays attention only to what's in the currently visible stack frame. None of this stuff is doing anything. All this stuff is hibernating for the long computer winter in case we ever go back to those functions that we're calling. And remember again, this is like function A called function B, called function C, calls function D. Function D is going to be the only one the system can see until function D finally finishes and returns, which it will never do if I don't stop talking and start writing. We're passing in P arrow next to this brand new function call here, and P arrow next when P is 100 is big fat goose egg 0. Here's why we don't test the water. We don't stick our toe in and test the water before we call this function. This, I'm going to use a different color. That's what stops it. We don't check, we don't look before we leap. We go ahead and jump off the edge. This is called a base case for the recursion. The base case, the bottom out, stop, go no further. Look what happens. If P is 0, return. P is 0, we're going to return. Now before I forget the labels, that's the base case. This has a name as well. Where you call the function, that's the recursive case. Why make a big deal about the terminology? Your base cases have to precede your recursive cases. You've got to check and make sure that you are in a legitimate place with your recursive function calls before you try to do anything with the data that was sent into you. This has got to stop the madness here and get out. If they passed us a 0 pointer, for example. Well, it's not for example, it's for real in this one. They passed us a 0 pointer. This would crash the program if we let it fall through to the recursive case and do some business here. If P is 0, P arrow data is an access violation, it'll crash the program. I guess for consistency, I better make that a rust-colored square bracket as well. There. Base case is where we test that there's no more work to do and we get the heck out of here. Recursive case is when we stick around and maybe do a little work and then call ourselves. That's the recursion. So what have we got here? P is 0, return. It pops the stack frame. What's the significance of that? When it pops the stack frame in return, where does it return to? It returns to the previous call. Listen to this very carefully. It returns to the previous call that thinks the rightful value of variable P, in fact it is. The only value that's visible of variable P is the address A00. So it returns back to the previous function call, not all the way back to the beginning, certainly not back to the main program. It returns to the previous function call, comes back where it came from, right here. And what does that do? Well, that terminates normally. That's the end of the function. So it goes back to where it came from and pops that stack frame off the top of the stack. The stack is upside down, remember. The memory addresses get lower and lower as we push things onto the stack. But it pops off the stack that thought that the value of P was supposed to be A00 and reveals what? We go back to where we came from. Now we're back to this function again that looks just like all the other calls, except this function is the one that thinks the value of P is rightfully hexadecimal 500. This one thinks the man of the hour is Larry with P equal to hex 500. There's nothing left to do there. Pop. It comes back to here. This thought the rightful value of P was FF00. That was where we started. That was the first recursive call. There's nothing else to do. Pop. Now, just in case that was just all so easy, all that trace, of course, I'm insulting your intelligence. It just all makes perfectly good sense. Here's some thought experiments for you. Play along, if you will. I'm going to leave the base case there. I do not want infinite recursion, and yeah, that's a closing curly bracket. It looks so pathetic, doesn't it? What if? Is it going to crash the program if I swap these two around? I do the recursive call first, and then do the cout? I'm pausing so you have time to think about that. You figured it out. If I swap these two, look what happens. I call deeper and deeper and deeper and deeper. It keeps calling itself and calling itself and calling itself, setting up these new stack frames without printing anything out. Just before it gets to the cout statement, it makes a recursive call without printing anything. So you might think it produces no output at all. Except when we get to the base case and p is 0 and it starts returning, when it returns back to this function call, which is now that line, the next to the last rather than the last line, then as a parting thought on the way out, then it prints out p arrow data. Here's the solution to your thought problem puzzle. All I have to do is swap those two lines and it prints out the list backwards. It makes recursive calls all the way down to the bottom of the list and doesn't start printing things out until it's way back out of that recursive call sequence. So it would print out Curly, Larry, Mo. You see how that would work? What if, now I'm actually going to change it for this what if. What if I do this? Cout less than p arrow data. Like that. In other words, I copied and pasted rather than moving, rather than cut and paste. I've got the same cout line down here as the last line of the function rather than strictly the next to the last line of the function. So I do two couts in the function. This one prints out on the way down. It'll print out Mo, Larry, Curly, and then on the way back out, it will return to Curly and print out Curly again. Then as it's coming out of the next call, it prints out Larry. And on the return from that, it prints out Mo. So we get stooges going and coming. That was a lot to pile on in the last minute and a half of this video. But those are the sorts of thought experiments that you want to run through your own mind when you're looking at these and trying to figure out what the hey is going on with this gigantic multicolor mess. I hope that trace is useful. We will talk about this at our required class meeting on Friday. So I hope you've got all the videos caught up by then. Otherwise, oh my goodness, this is going to blow your mind, isn't it? I'll see you online.